Okay, let's take a look at section 8.3. So for 8.3, we're going to use what we learned in 8.2 about compound inequalities and apply it to absolute value equations and inequalities. So before we jump into the inequalities, let's go ahead and define what absolute value is. So remember, absolute value is just the distance from zero. So if we have a number line here, let's put 0 in the middle. And then I'm going to go out to 3 on each end, so 3 and -3. If I were looking at the absolute value of 3, this is saying how many units is 3 from 0? Well, 3 is over here, and it is 3 units from 0. But it's the same thing if we have the absolute value of -3. -3 is over here, and so the absolute value of -3 is also 3. Because whenever we're talking about distance, distance is always positive, which means the absolute value is always positive. And so this is really important to keep in mind when we start looking at some of the special cases at the end of the section. So these first couple of examples, we're going to be talking about absolute value equations and inequalities, and these are going to be kind of an introduction into both of those. We're not actually going to solve anything, but we are going to graph the solution. And so number 1 here, we're given the absolute value of x is equal to 8. And so what this is saying is that some number has a distance of 8 units from 0. Because if we take a look at this expression here, absolute value is distance. So the distance for some number from 0 is 8 units. And so if we were to go ahead and graph this one, we're always going to use a number line. I'll put 0 in the middle. Some number has a distance of 8 units from 0. So if you notice, we could have the number 8. So we're going to put a point there. But what other number has a distance of 8 from 0? -8. So we're actually going to have 2 points here. We're going to have 8 and -8. And this is our graph for this one. I'll go ahead and box that. Now let's go ahead and try a couple more of these. So let's say we have the absolute value of x is less than 8. So this is saying that some number has a distance of, fix that, less than 8 units from 0. Okay, so now let's go ahead and take a look at this graph again, and I'll put 0 in the middle. We're still looking at 8, so let's put 8 and -8. Now, if we know that this number has a distance of less than 8 units from 0, that could be the number 1, because the number 1 has a distance of 1 from 0, which is less than 8. It could be the number 2, 3, 4, 5, 6, or 7. But it can't be 9, because 9 would have a distance of more than 8 units from 0. So it's any number between -8 and 8. And we don't want to include 8. So just thinking back to inequalities, we're going to put parentheses at both of these endpoints. If it had been a less than or equal to, then we would have had brackets at each one of these. And pay attention to what the graphs look like. So for a less than, we had everything in between. For a greater than, so x is, or the absolute value of x is greater than 8. Again, this means, I'll squeeze this in over here, some number has a distance of more than 8 units from 0. And so with this graph, we want all of the numbers that are more than 8 units from 0. So instead of shading in between -8 and 8, we want everything that's further away, further than 8 units away from 0. So everything to the right of 8 and everything to the left of -8. So this one, if you remember back to 8.2, putting in parentheses because it's a greater than, not greater than or equal to, this one looks like the graph of an or. So a greater than is going to be the outside parts in general. There will be a couple of special cases. But less than, in between, greater than, outside pieces. So let's start talking about absolute value equations first. And then we'll get into those absolute value inequalities. So absolute value equations. So let's look at the general form first. We're going to have the absolute value of ax plus b. So we're just going to have something linear on the inside is equal to k. So what we're going to be doing, because if we think back to what we did over on this one, this is saying the absolute value of x, or the absolute value of some number, is equal to 8. And we got x is equal to 8. And x is equal to -8. We took what was on the inside of the absolute value and set it equal to the positive and negative version of what we had on the right. So what we're going to do is we're going to take what's on the inside and we're going to split this up into ax plus b is equal to positive k and ax plus b is equal to negative k. We're just splitting up our equation into two separate equations, only change the sign of k, so the number on the right, never change the sign of the stuff on the inside. So let's go ahead and look at some examples. And for these examples, we're going to go ahead and solve and then graph the solution. You won't always have to graph the solution, but we're going to, just so you can kind of see how it works. First one here, let's take a look at the absolute value of 4x is equal to 20. So this is saying that some number is 20 units away from 0, so it could either be 20 or -20. So we're going to take whatever's on the inside of the absolute value, so this 4x, oops, and it can be either be equal to 20 or 4x could be equal to -20. Change the sign of the number on the right. Do not change the sign of the stuff on the inside. So if we go ahead and solve each one of these, we have two nice linear equations. I'm going to just divide both sides by 4, and we get x equals 5. And divide both sides by 4 on this one, and we get x equals -5. These are our two solutions. So if we were to plug this back in, to always double check your work, if we have our equation, the absolute value of 4x equals 20, well, we have the absolute value of 4 times 5 equals 20, and that gives us the absolute value of 20 equals 20, which is true. 20 is 20 units away from 0. And if we check our other equation, the absolute value of 4 times -5 equals 20. Well, 4 times -5 is -20, and the absolute value of -20 is also 20. Either way it works out, so that's one way you can kind of double check your answers here. Now, if we were to go ahead and graph this one, the graph isn't super important for these, but you might see a couple of them on the homework. All we're going to do is place 2 points, one at -5, and I'll normally put 0 in the middle, and one at 5. So our solution is just 2 single points because it's an equation. If it were an inequality, that's when you have kind of the shaded regions. But this is our graph for this one. Okay, let's take a look at another one. The absolute value of x plus 2 equals 3. All right, so again, first thing we want to do is split this one up. And notice how the absolute value is by itself. We will see a couple of examples where you have to get the absolute value alone first. But we can go ahead and split this up straight away. So we get x plus 2 equals 3. And then x plus 2 equals -3. So just change that right side to a negative. And now solve each one of these. And subtracting 2, we get x equals 1. I'm going to box that. And subtract 2 on this one. And -3 minus 2 is -5. So we get 1 and -5 as our two solutions. Notice how they're not always going to be opposites of each other, but if we were to plug them back in, we'd have 1 plus 2 is 3. Absolute value of 3 is 3. Plug in -5 and we get -5 plus 2, which is -3, and the absolute value of -3 is 3. So not always opposites of each other, so be careful with that. And again, if we were to graph it, I'll put, if you wanted to just do 1 and -5, you could. I'll put 0 in the middle, 1 on the right, -5 a little bit further over to the left, and again, just 2 points there. Absolute value equations in general are pretty nice compared to absolute value inequalities. Let's just do a couple more of these. Number 3. Let's go ahead and do the absolute value of 5 minus 3/5 k equals 11. So first thing, oh, that 11 does not look good. Let me change that. First thing we want to do, again, absolute value is alone. So let's split this up. We get 5 minus 3/5 k. Again, we're not changing the signs of the stuff on the inside, equals 11. Now we have 5 minus 3/5 k, whoops, equals -11. Just change the sign of the number on the right. Now, if we go ahead and solve for k, we could get rid of the fraction first. We could multiply everything by 5, or you can deal with that at the end. I'm just going to deal with that at the end for this one because it's just one fraction. So let's subtract 5 from both sides. We get -3/5 k. I keep putting the k on the bottom. There we go. -3/5 k equals 6. And now to get rid of this fraction, remember to get rid of a fraction, we can multiply by the reciprocal. Make sure it's the same sign though, because negative times a negative is a positive k, which is what we want. So multiply both sides by -5/3. So everything should cancel on the left side. We get k. On the right, I'm going to write this as 6/1. So on the top, we get -30. And remember, you can multiply and then reduce, or reduce first. Doesn't really matter for this one because the numbers are pretty nice. If we multiply first, we get -30/1 times 3 is 3. And that's the same thing as -10. And on the right side here, if we go, I'm going to go ahead and move this one over just to give us a little bit more room. If we go ahead and subtract the 5 from both sides, we get -3/5 k. Oh, every single time. -3/5 k equals -16. Multiply both sides by -5/3. And again, on the left side, everything should cancel nicely. So we get k equals. Now for this one, the numbers are a little bit bigger, but if you notice, we can't actually reduce anything. 3 doesn't go into 16, 3 doesn't go into 5, so we're gonna have to multiply. 10 times 5 is 30, 10 times 5 is 50, I was getting ahead of myself. 6 times 5 is 30, 50 plus 30 is 80. So we have negative 80 over 3. And if you want to leave it just like this, that is perfectly fine. You can change it to a mixed number if you want. It makes graphing a little bit easier. So if we were to go ahead and divide 80 by 3, you can always divide off to the side. Remember, no calculators in this class. 3 goes into 8 twice. Subtract. 3 goes into 26 times. And we have a remainder of 2. So it's going to be 26, negative 26 and 2/3. Either answer is perfectly fine. This improper fraction is actually easier to type into my MathHub, so I would recommend leaving it like this guy. But if we were graphing, which we are, that bottom number is a little bit easier to graph. So furthest left is the more negative number, so negative 26 and 2/3 on the left, and I'm just going to put these two numbers here. Negative 10 on the right. If you wanted to put 0 over here on the right, you could, but you don't need it. You can just put these two numbers. And that's our graph. All right, let's go ahead and try just one more of these. And let's go ahead and I'm gonna erase this here. And we'll put number 4 over here on the right. This one's a little bit nicer than number 3. There's no fractions to deal with. But this one we're given the absolute value of 5x plus 2. And then on the same side of the equal sign, minus 9 equals negative 7. Couple things to notice here is that the right-hand side is negative, which we'll see some special cases later when we have a negative on the right-hand side. This is not a special case because what we're going to do first actually is get the absolute value by itself. So first thing I'm going to do is add 9 to both sides. So we have the absolute value of 5x plus 2. Remember, we didn't split up the equation yet. All we did was move the 9. So the absolute value is still there, equals positive 2. So the right side is now positive. So that's a good sign. We always want positive right-hand side. And now if we split this up, we have 5x plus 2 equals positive 2. Change the sign and we get 5x plus 2 equals negative 2. So thing for this one is you want to get the absolute value alone first. So before you do any, wow, that exclamation point did not work out. Before you can do any splitting up of the equations, you want to make sure that the absolute value is completely by itself. You're just going to do that by moving the other term over to the right side. But now, two regular equations. So let's subtract 2. We get 5x equals 0. Divide both sides by 5, and 0 divided by 5 is 0. So x equals 0. And on this other one, let's subtract 2 again. We get 5x equals negative 4. Divide both sides by 5, and this one, there's no reducing, and 5 doesn't go into 4, so I'm just going to leave it as a fraction. So negative 4/5. Now, if we go ahead and graph this one, again, we just have these two numbers. One of them is actually 0, which is perfectly fine. Just make sure 0 bigger than any negative number, so it goes on the right. And we're going to put a point at negative 4/5 and a point at 0. Again, if you wanted to check this, take your two numbers and plug them back into the original equation. Make sure it goes into this one just in case you made a mistake on moving that number to the other side, or maybe you split it up early. Always make sure you plug it into the original equation. Okay, so that's absolute value equations. Now let's go ahead and take a look at absolute value inequalities. So this is where it starts to get a little bit trickier. And there's kind of two rules to remember, because if you remember with inequalities, we either have a less than or a greater than, or less than or equal to, greater than or equal to, but those two cases are kind of combined. So let's write down our two cases. So one is if we have a less than. And for a less than, what we're going to do is if we have ax plus b, the absolute value of ax plus b is less than k, or the absolute value of ax plus b is less than or equal to k, these fall under the same case, we're going to kind of split this up into, or turn this into a compound inequality. So you're going to take what's on the inside and then bring down that less than k on the right. And then on the left, we're going to have a less than negative k, or negative k is less than ax plus b. This is the important thing here. You can think of this like an and inequality or a three-part inequality. Same thing if you have a less than or equal to, take what's on the inside, put less than or equal to k on the right, and then match that on the left, except with a negative k. So notice how we're still using the positive and negative k, but now we're turning it into a compound inequality. Same thing with the greater than, except this one is, you can think of it like, the way I like to remember is great or than. So what I mean by that is if we have the absolute value of ax plus b is greater than k, or the absolute value of ax plus b is greater than or equal to k, we're going to take this and we're going to split it into an or inequality. So this first one is going to become ax plus b, keep the original, so greater than k, or ax plus b. Now we're going to change the sign of k to negative k. And remember, when you multiply by a negative, you have to flip your inequality. So that becomes a less than negative k. Same exact thing with a greater than. You're going to have ax plus b, keep the original, greater than or equal to k, or ax plus b, flip the inequality, change the sign. So less than or equal to negative k. The big thing here is if it's a greater than, it's an or. If it's a less than, it's an and. So we write it as a compound inequality. Now, let's go ahead and look at some examples here, because these ones are where it gets kind of tricky. But if you can remember these two cases, that's going to help you a lot. So we're going to solve, graph, and how do you think we're going to write our solution now that we're dealing with inequalities? We're going to write the answer in interval notation. Always using interval notation for inequalities. So number one here, let's look at one that's it's just like one that we saw at the beginning. So we're going to kind of revisit this one. The absolute value of x is less than 8. So this is a less than, it's an and. So we're going to write it as one of these compound three-part inequalities up here. So we're going to take whatever's on the inside of that inequality, bring down the less than 8, and then on the other side, we're going to have a -8 is less than x. So all this is saying is that x is between -8 and 8. So remember, for the graph for these, we have the number line. We're going to put -8 and 8, parentheses or brackets. We're going to use parentheses because they're less than, not less than or equal to. And we're going to shade in between because it's between -8 and 8. Now, remember, actually, let's do the interval notation, then we'll take a look back at one of those first examples we saw. Our interval notation, going from the furthest left to the furthest right, we're going to start at -8 with a parenthesis, comma, the furthest right we go is 8 with another parenthesis. So if we go back to that first, it was the second problem actually that we looked at, back on page 1 here, we had the absolute value of is less than 8. This is saying some number has a distance that is less than 8 units from 0. We shaded in between. Same exact problem over here. We shaded in between. We just saw it in a slightly different way because this is how we're going to have to do it when we have something other than just an x, because we'll have to do a little bit of solving. So let's go ahead and take a look at some more of these. Number 2. Let's go ahead and do the absolute value of x plus 2 is less than 3. So again, identify first if you have a less than or a greater than. We have a less than, so we're going to make our 3-part inequality. So we're going to keep the x plus 2, keep the less than 3, and then we're going to put in the less than, and then -3 on the left. And this is all because we have a less than right here. Now, if you remember with 3-part inequalities, our goal is to get x in the middle by itself. And so in order to do that, we want to subtract the 2 from the middle, the left, and the right. We have to do it 3 times. So in the middle, these cancel, we're just left with x. Bring down your inequalities, and -3 minus 2, -5. 3 minus 2 is 1. And now if we go ahead and graph this one, we're going to have -5 and 1 as our 2 numbers. And we're going to have everything in between -5 and 1 because x is between these 2 numbers. So let's put parentheses because it's just less thans, and shade in between. And so our solution here, we're going to have -5 with a parenthesis, comma, up to 1 with a parenthesis. So any number between -5 and 1 is a solution to this absolute value inequality. And that's one way you can kind of check your answer is, let's say you pick 0. If I were to plug 0 in here, we have the absolute value of 0 plus 2 is less than 3. The absolute value of 0 plus 2 is the absolute value of 2. And the absolute value of 2 is 2, which is less than 3. So that's one way you can check and make sure that you shaded the right part, because sometimes you'll be shading the outside pieces if it were an or. So I recommend always checking these. It's going to really help you kind of make sure that your answer is correct. Okay. One thing I do want to show you with this one, we had the absolute value of x plus 2 is less than 3, and we got -5 and 1. Now, if we go back to our other examples, it was the first or second one with the equations, we had the exact same kind of equation, but this time it was an equal sign, not an inequality. Notice how we also got -5 and 1. you should get the same type of numbers as if you had an equation, but instead of having two distinct points on our graph, we had an entire shaded region. That's the difference between inequalities and equations. Okay, let's go ahead and look at some more. Let's see if I have another less than. Yeah, let's go ahead and do the absolute value of 3x plus 2 plus 4 is less than or equal to 15. Okay. So the big thing to remember for this one is before you can split up your absolute value equation, just like we saw back here on number 4 on the right here, we had to get the absolute value alone before we could split it up. Really similar idea with this one. Before we can change it to a compound inequality and get rid of the absolute value, we need to get this absolute value alone. So first thing I'm going to do is subtract this 4. And so we have the absolute value of 3x plus 2 is less than or equal to 11. And now we can make our compound inequality. So because it's a less than, we're going to make our 3-part inequality. So we have 3x plus 2 less than or equal to 11. And on the left side, we're going to have a less than or equal to and a negative 11 over there. So it's now solving for x, we're going to subtract 2 from all 3 sides. We have negative 13 less than or equal to 3x less than or equal to 9. And then if we divide all 3 sides by 3, we get negative 13 thirds, and I'll leave it just like that, less than or equal to x less than or equal to 9 divided by 3 is 3. Now it's solved, we can go ahead and graph this. So we have negative 13 thirds on the left, 3 on the right. And because we have a less than or equal to, we have brackets. So I'm going to have brackets and shade in between. And then our interval notation, we're going to start at negative 13 thirds with a bracket, comma, we're going to go all the way to 3 with another bracket. And notice the kind of theme here with a less than or less than or equal to, you're always shading in between. And your brackets and parentheses should always be the same because you have to write that left one in according to what you have in the original equation or inequality. Now let's go ahead and see what it looks like with a greater than. So number 4, we're given the absolute value of x plus 2 is greater than 3. So this one's just like the other two that we've seen using x plus 2 and 3. So just like with this one here, number 2, we got negative 5 and 1. We should have something kind of similar. So let's go ahead and look at this. So because it's a greater than, this is an or, which means we can't write it as a single inequality. We need to write it as 2 separate inequalities with an or in between. So we're going to keep the first one the same, but without those absolute values. So x plus 2 is greater than 3, or now we're going to keep the x plus 2. Remember, that doesn't change, but we're going to flip our inequality and make that a negative 3. So you're always going to flip inequality and change the sign of the right-hand side. So RHS is right-hand side. Okay, now if I solve both of these, I'm going to subtract 2. We get x is greater than 1. So we got that 1 again. Or subtract 2 here. We get x is less than negative 5. got that -5. Now, if we graph this, we're going to have, make sure you put them in numerical order. So -5 on the left, 1 on the right. And so x is greater than 1. We're going to have everything to the right of 1 using a parenthesis. X is less than -5. We want everything to the left of -5 with a parenthesis. And remember with ors, you can satisfy one or the other, which is why I put this on the same number line, because we're not looking for the intersection. We want these two outside pieces. And so if we go ahead and write the interval notation, if you remember for this type of graph here where you have two separate pieces, we're going to have two intervals. The left interval is everything from -infinity with a parenthesis to -5, also with a parenthesis. Union, so whenever you have those two separate intervals, you're going to put the union in between. And then the right inequality is everything from 1 with a parenthesis to +infinity. So to check this one, you could take a number that's less than -5, so let's say -6, or a number that's bigger than 1, let's say 2, and it should satisfy this original inequality. And this is our solution. And now if we go back to our original problem here, going back to page 1, when we had a greater than, so here in number 3, we shaded the outside pieces because we had some number with a distance that was greater than however many units away from 0. Same thing over here when we have a greater than. Most of the time, unless we're looking at a special case, you'll be shading these outside pieces. So less than, in between, greater than, outside. All right, now let's go ahead and look at just a couple more of these. Let's go ahead and do the absolute value of 7 minus 4x is greater than or equal to 7. And again, it's an or because it is greater than. So let's go ahead and split this up. So we're going to have whatever's on the inside, 7 minus 4x, keep the original, so greater than or equal to 7, or keep the inside the same, 7 minus 4x, flip the inequality, change the sign. So less than or equal to -7. Now, if I go ahead and solve this, let's subtract 7 from both sides. We get -4x is greater than or equal to 0. Now, when I divide both sides by -4, if we divide by a negative, what do we have to do? We have to flip our inequality. So we actually get x is less than or equal to 0. Solving our other one, let's subtract 7. We get -4x is less than or equal to -14. Divide both sides by -4. And we get x is, we divided by a negative, so we'll flip. And a negative over a negative is a positive. And I'm going to reduce this down by 2. So we get 7 over 2. Now, let's go ahead and graph this. Remember, this is an or. So we can go ahead and graph it on the same one. We're not looking for the intersection. That's an and. So we're going to have 0 and 7/2. 0 on the left, 7/2 on the right. Now, x is less than or equal to 0. We're going to have a bracket, shade to the left. X is greater than or equal to 7/2, bracket, shade to the right. And I'm always going through these individual steps because you will get a couple of special cases where it's not going to be the outside pieces. And so we'll see one like that coming up soon. Now, let's go ahead and write our interval notation. So our interval on the left, we have everything from -infinity, parenthesis, to 0 with a bracket. Union, join those two together. Everything from 7/2 to infinity. and that's our interval notation. And again, you could pick any number less than 0 or greater than 7/2. Plug it into the original up here, and it should be a solution. Okay. All right, so if we go ahead and look at some of the special cases. Actually, before we do that, I want to look at one more. This is number 6. Just so you guys see this one. We're given the absolute value of x plus 2 minus 3 is greater than 2. So think back to the other problems where we had something else other than the absolute value on the left. First thing you want to do is get the absolute value alone. So whether it's an equal sign, if it's a less than or a greater than, always get the absolute value alone first. So let's add the 3. The absolute value of x plus 2 is greater than 5. Now we can split this up, and because it's a greater than, it's an or. So we're going to have x plus 2, keep the sign, so greater than 5. Or, now if I keep the stuff on the inside, so keep x plus 2, change the sign, flip the inequality, change the sign, so less than -5. Now let's solve this and graph it. I would do this one by yourself because we've done a couple of these. So let's subtract the 2. X is greater than 3. Subtract the 2 on the right. So we get x is less than -7. Now if we go ahead and graph, I'll put the smaller number on the left, larger number on the right. X is greater than 3. We're going to have a parenthesis shading to the right. Again, double check that it is the outside pieces, and you'll see why in a second. In our next examples anyway. X is less than -7, parenthesis, shade to the left. And so with our interval notation here, we have everything from the furthest left, which is -∞, with a parenthesis, to -7. Union, join those guys together. Now we're at 3 with a parenthesis, shade all the way to the right, which is +∞. So once you get a little bit of practice with those, they're not too bad, but they are kind of tricky. As long as you remember how to set them up. So greater or greater than or equal to is an or. And if you have a less than or a less than or equal to, that's when you make it into a 3-part inequality. Those are kind of the 2 big things for those. So now let's take a look at some special cases. And for these special cases, we're not actually going to have to go through and do all of the work. And you'll see why in the first couple of examples. If you were to go through and do all of the work, you have to be careful with the graph. And we're going to solve and then graph if given an inequality. So if it's an equation, we're not going to graph these. So number 1 here, we're given the absolute value of 6x plus 7 equals -5. First thing to always check is that your absolute value is alone, which it is. Now there's something wrong with this equation, which makes our answer really nice and fast. The problem here is that we have an absolute value equal to -5. Remember that whenever you take the absolute value, so if we have the absolute value of 5, we get 5. The absolute value of -5 is also 5. There's no way we can get a negative over here on the right. So this one has no solution. Or the way that they'll write it in my math lab is with the empty set. That's because absolute value cannot equal a -5. number. And this is really important. So anytime you're given an absolute value equation equal to a negative number, make sure the absolute value is alone, just in case when you move something over, it makes it positive. In that case, it's fine. We saw one like that. In this case, if the absolute value is alone and it's equal to a negative, it has no solution. That one makes it nice and easy. Let's take a look at another one. Absolute value of 7x plus 12 equals 0. Now with this one, it's not equal to a negative number, it's equal to 0, which is actually perfectly fine because the right-hand side has to be non-negative, meaning it could be a 0 or a positive number. But if we were to split this one up, we get 7x plus 12 equals 0. And then remember in our other equation, we would change the right-hand side, change the sign of it to the opposite. But negative 0 doesn't exist because the opposite of 0 is still 0, which means we have two equations that are exactly the same, which means how many solutions are we going to have? We will only have one solution. So there should be a question on your homework asking about if the right-hand side or this value of k is 0, how many solutions? We would have one, which we'd get from solving this equation. So let's go ahead and do this really fast. Let's subtract 12. We get 7x. I was going to put a k. Wanting to write k's everywhere. Equals negative 12. Divide both sides by 7, and we get x equals negative 12 sevenths. So we can get negative numbers as answers, but we can't have negative numbers on the right. And if you have 0 on the right, you only have one solution. It's a little different when we have inequalities though, and we'll see that in a second. Couple more special cases. Let's say we have the absolute value of x is greater than negative 1. So anytime you see a negative on the right-hand side, think that you have some kind of special case, either 0 or a negative number. That'll give you a special case. So if it's a greater than negative 1, well, we know the absolute value is positive. And any number greater than negative 1, so all of the positive numbers are greater than negative 1. And so since all of the positive numbers are bigger than a negative number, this one is going to have an infinite number of solutions. So if we have something greater than a negative, greater than a negative number, this means that we're going to have an infinite number of solutions, and so our solution is negative infinity to infinity. The other way to think about this one, if you saw this and you completely forgot that this was a special case, if we were to do the work for this one, it's a greater than, so it's an or, so we'd have x is greater than negative 1, or x is, flip the inequality, change the sign, so it becomes x is less than 1. If we were to graph this, we'd put 1 and negative 1. X is greater than negative 1. We're going to have a parenthesis, but we're shading to the right. So this is why you have to be careful with your graphing, because in this case, it's not the two outside pieces. It's actually going to be the full number line, because x is less than 1 is a parenthesis going to the left. And so we get the full number line, which gives us that negative infinity to infinity. These parentheses kind of disappear with your graph. So this is if you were to go through and work it out, but if you can remember that it's a special case, you can go straight to your solution. This next special case is a little bit nicer. The absolute value of x is less than negative 5. Well, we know that absolute value can't be negative. So it cannot equal a negative number. And every single number that is less than -5 is also negative. So that means that this solution is not possible, which means we have no solution. Or like on your homework, you'll see the empty set, because absolute value, keep combining my U and my E. Absolute value cannot be less than a negative number. That's just because all numbers that are less than a negative number are also negative, and we can't have a negative absolute value. Okay, so now let's take a look at our last special case. And remember, special cases arise when you have a negative number or 0 on the right-hand side. So if we have x plus 2 is less than or equal to 0, sorry, the absolute value of x plus 2 is less than or equal to 0. If we take a look at this one, we know that absolute value cannot be negative. So absolute value cannot be less than 0 because all of the numbers less than 0 are negative. But, wow, I cannot write today. But absolute value can be equal to 0 because you can have a number that's 0 units away from 0. That is 0 itself. So what we're going to do is we're going to take this and we're going to get rid of the less than part, and we're just going to have the absolute value of x plus 2 is equal to 0. And this takes us to one of our other special cases. So remember, if you have something that's equal to 0, and if we were to split this up, we would get x plus 2 equals 0. Change the sign, you get x plus 2 is equal to 0. Those are exactly the same. So we don't need to look at the second case because there isn't one. So if we solve this, subtract 2, we just get x equals -2. We just get a single digit answer. If you had x plus 2 is greater than or equal to 0, that one is one where you have to actually go through and do the full work, because a number, so let's say we had the x plus 2 is greater than or equal to 0. This is not a special case. The reason for that is because absolute value can equal 0 and absolute value can be greater than 0. So that one, they both actually work. That one you'd have to go through and do the full split it up into ORs and then graph it. So be careful with those. The special cases don't come up a ton, but they are in the homework. So keep an eye out for those. Make sure whenever you have a negative number or 0 on the right, you probably have a special case, except for this case, in which you don't. So that's 8.3, kind of tricky compared to the rest of chapter 8, but section 8.4 is review, as is section 8.5. So that stuff should be pretty nice and easy for you guys as long as you remember it.